Hey, how's it going? Um, this is for people who sort of ended up on this video randomly online. Um, this is part of a club called TOM. It stands for Tikkun Makers. It's a club in Georgia Tech and other schools and like other countries too, I think, where we meet up with um clients, local clients who have physical or sensory impairments, disabilities, and we try to make we work on projects that they sort of would like to have but don't quite have, so like shortcomings in current assistive devices that are in the market, for example. So we're making a device that is able to measure how much water is in a cup. Our goal is to um track how much water someone drinks. And for people who have dementia, it it turns out to be that it's common for them to stay dehydrated because they don't, maybe they forget when they drank water the last time. And we are building something that reminds people to drink more water, basically, if they didn't yet in the day. And this is going to cover some of the electronics side of things. Um, so we are thinking about using a force sensitive resistor, which is a resistor that changes how much resistance it has, electrical resistance, based on how much force it has applied to it. So yeah, this is a really simple drawing of it. I want to show you a real photo of what it looks like. So, okay, so this is what it looks like, and it has a circular part that's going to be the main part where the force is applied to, and the long like rectangular parts, I think you can ignore. Um, this image shows how it's made. So it's made of like three main layers. One is, well, so the working principle of this thing is it's a circuit, electrical circuit that is separated by a tiny air gap between the top and the bottom layer. And the more someone presses on it, the less air gap they have. And so the more conductive it gets. And so we can use that to effectively measure force. And yeah, so the middle part here is where that air gap is. The vent is where air moves through in and out. Middle part, I think, is where the input is, I think, and the top part is where the output is. So yeah, and these have roughly linear relationship or logarithmic relationship with force and resistance. So here's a log charts, log on both x and y axis. We can see, for example, when there's 10 grams of force, the resistance is so high that it sort of escapes the graph. But when it's 100 grams, the resistance is about 7, 8 kilo ohms, which is uh, it's not like well, it's not like crazy high. And when we go up to 1,000 grams or 1 kilogram, it's about, I would say, 1 kilo ohm. So roughly like the force change from like 0 to 1 kilogram results in like 7, 8 times change in the resistance. But yeah, and cool. So that's it. And the key thing to remember is that it has a variable resistance, and that's how it works. So by default has a high resistance, and when it's loaded has a low resistance. And to use any type of sensor, you sort of make what's called an instrumentation circuit. It's a fancy way of saying a circuit to like actually measure it. Um, to like how to supply electricity, how to measure electricity, stuff like that. And it's really simple for our case, but for more advanced types of sensors, it gets more messy, more complicated. But yeah. And here's a little simple circuit that I think can be used to measure our thing. Measure how much force is applied to the resistor, FSR. I'm gonna call it FSR from now. And you can see a voltage source. When we're actually building this is gonna come from the microcontroller, and it's probably gonna be something like 5 volts. Because most microcontrollers turns out they oh, they have either 5 or 3.3 volts. It's just sort of the convention. And we have a current defined as like going clockwise. And there are two resistors here. The normal resistor looking thing here, RC, it's going to be a resistor that has a constant value. And the second one, our FSR, we're going to call it to have a resistance of RV. The reason why we have two instead of one resistors is um let me show you with a simple interactive example. 1 second. Cool. So yeah, let's build a circuit that has so this is a online circuit simulator called Circuit Lab, and it's really cool. It works well. It's super simple. I don't think you can do like really complicated things on it, but I would say this is a lot more accessible and like easier than building an actual circuit. So um, use it if you are interested. So we have a resistor here, voltage source. Let's give it 5 volts. And this has 100 ohms by default. And I'm going to measure how much voltage drop it has um, with a voltmeter. And what I mean by voltage drop, if you are not familiar already, is a circuit has varying resistor or varying voltage throughout its like path. So this is a voltage source, and what it means is um it increases voltage by 5 volts, right? By the way, voltage is always sort of defined relatively. It's a relative term. Or like it's a relatively defined quantity, and like it's only possible to measure the difference in voltage between two things. There's like no zero, like no like fundamental zero in the voltage world. For like temperature, there is an actual voltage, or there's an actual zero, um, the absolute zero temperature, but it's not a thing. Similarly, like position is something that's defined relatively, because like you need a reference to measure position. You could make that the ground for measuring height. You can make that, like any arbitrary space in like X and Y coordinates that's not in the direction of height. But yeah. So here's a circuit that has one resistor, right? And by the way, it's really only practical to measure voltage. It's pretty impractical to measure current, and I'm pretty sure it's impossible to like directly measure resistance. So, when we measure something, when we like, use any type of sensor, it's going to be measuring voltage. That's gonna be how it works. And the problem with having one resistor is when we change the resistance, the voltage doesn't change. It's gonna be the same as the input voltage always. By the way, this is like the voltage that the voltmeter measures. So, we went from 100 ohms to 1,000 ohms. We went from 1,000, we can go to even more. It's gonna be the same 5 volts. But if we add one more resistor here, you see that it changed a little bit. The reason why is um, the voltage starts out at 0 here in the ground, and it goes up by 5 volts, and it drops a tiny bit by a 100 ohm resistor, and then it drops, uh, and by a tiny bit, I mean 0.05 volts, right? And it drops the rest of the remaining volts. It goes back to 0 here. So yeah, it's 0 here, 5 volts here, drops to 4.95, drops back to 0. And if we increase this, we'll see that the amount or the ratio between the voltage drop sort of changes. So this resistor, because it now has more resistance, it will contribute to more voltage drop. And if you make this same amount, we'll see that it starts at 5, goes down to 2.5, which is half, right? And it makes sense because these two things have the same resistance, right? And goes back to 0. This is really simple things, right? But I think it's easy for us to take stuff from like circuits class and then apply it to the real world. Um, yeah, stuff feels confusing, and just want to make this clear. And let's go back to our notes. So this circuit in the center, it's super similar to what we just saw, has two resistors, and we demonstrated that the ratio of resistance between the two um, translates to the amount of voltage drop in one of the resistors. And more concretely, this can be calculated with like basic circuit analysis techniques. One's called Kirk Kirk. I don't know how to pronounce this guy's name. Kirchhoff's voltage law, often called KVL, and it means that a loop's ending voltage is always 0. And again, this is because voltage is always relatively defined. You need to define 0 somewhere. And um, what it also tells is that uh, any circuit is going to like adjust how much current it has to make sure that the ending voltage is zero instead of uh like a positive or negative ending voltage because yeah, I don't know how to explain that. Look it up. But so that's the first part. And um we can use the KVL equation to determine how much voltage drop each thing is going to have. So I here is current measured in amperes or amps. V in is going to be how much source voltage. It's going to be 5 volts again. And RC and RV are resistance. So yeah. Um, so IRC is going to be equivalent to VC. And what's meant by VC is the voltage drop across resistor C. And VV is going to be how much voltage drop um, is across the resistor V. And they're always going to add up to V in, which is why there's like an equal sign that makes it equal zero. The entire equation equals zero. And we know RC, we know RV kind of, or we're gonna know RC for sure, and RV is going to be what we want to measure. And we also don't know I, so we need to figure out what I is. And Ohm's law, you probably learned this in physics too, if you've taken it, um, states that V equals IR. And by rearranging it, we see that I equals V over R. So the amount of current through something is going to be the voltage across it divided by its resistance. In our case, our V is V in from the microcontroller, and our total is going to be just the sum of RC and RV. So we can combine these two equations and solve that VC is going to be this expression here. And um, yeah, I guess we would have, so we can measure this quantity and this will sort of be related to the amount of force is applied across the FSR. It's not going to be like directly that amount. As you can tell, there are like some weird things in the equation. But I'll just show you with the simulator again what this looks like. So for the FSR that we bought, um, when no force is applied to it, it's gonna have 20 mega ohms. And 1 mega ohm is equal to 1 million normal ohm. So these two things, um, they're different by an order of uh they're different by 5 orders of magnitude. And when there's like a lot of force applied to it, it's gonna have a resistance of 200 ohms. So let's go back and right. So this is RC, this is RV, and this is gonna be what we measure. And the microcontroller has something that is capable of measuring voltage. So we don't need to do, you know, anything else on it. So when there's no force applied to our FSR, we're going to see 750 microvolts. And that's equal to, well, um, that's super tiny. I think a micro is like, to the -6 orders of magnitude. So yeah, it's gonna be a super tiny amount. I think we can assume this is zero. And when we start to apply some force, let's say we move this to 20 kilo ohms. And there's going to be now 650 millivolts. Millivolts are not that small. This is going to equate to 0.65 volts, right? So we will be able to see this. And when it goes down to 2000 ohms, we'll see 3 volts in our microcontroller. And when it goes down to 200 volts or 200 ohms, that's going to be the maximum that this FSR is capable of having. We'll see 5 volts. So um, you can see that the amount of voltage that we see is roughly equivalent to the amount of force. Or I wouldn't say equivalent, but they are related to it. So when we have more force, we see more voltage. And let's say like, the FSR breaks down or something. And I was like, oh, 1 ohm. Our voltage measurement is going to be capped at 5 volts, which is nice. We don't want to like feed more than 5 ohms to our microcontroller because it might break something. So yeah, we can do this and um, we'll, the next thing we'll do is we'll build a prototype circuit to actually do all this and make a physical shell to hold these circuits and, you know, like actually make it a nice product. But yeah, I hope this covers the theory side of things. Oh, yeah. So something I forgot to mention is in practice, we will want to do like a fit, like a curve fitting sort of thing. So, we'll measure how much voltage it has when we give it 100 grams of force and we'll record it. We'll measure the voltage when we give it 200 grams, 300 grams, all the way up to like a kilogram. And then we would be able to like, fit an equation to those data points so that it's more accurate and we know exactly what um, force we have in the resistor. But yeah, that's it. Sorry, the explainers are sort of overboard. So, it's probably good to speed this through like 2 times. But yeah, this is it for the first part.